sklearn, neighbors, radius neighbors graph. Description. This function constructs the k-nearest neighbors graph for a given set of samples. It connects nodes that are within a specified radius of each other in the feature space. Inputs. X. The input data. Typically a 2D array of shape n samples. N features, where each row represents a data point. Radius. The radius within which neighbors are considered. Outputs. A sparse graph representing the neighborhood structure. The graph is represented as a sparse adjacency matrix, where each non-zero element indicates a connection between two nodes. The value of each non-zero element is 1, representing an undirected connection. The graph can be visualized using various plotting libraries like matplotlib. Steps. For each data point in X, it calculates the distances to all other points using a specified distance metric. It then identifies the neighbors within the specified radius. The neighbors are then connected in the graph with an edge weight of 1. Metrics. Distance metric. The choice of distance metric, e.g., Euclidean, Manhattan, Chebyshev, can significantly influence the resulting graph structure. Radius. The choice of radius determines the density of the graph and the number of neighbors for each node. Visualization plots. Graph visualization. The resulting graph can be visualized using plotting libraries like matplotlib or networkx. This visualization allows you to analyze the connectivity patterns and identify clusters or dense regions in the data. Scatter plot. A scatter plot of the data points with the graph edges overlaid can provide a visual understanding of the neighborhood relationships. Fine-tune parameters. Radius. The radius parameter controls the density of the graph. Increasing the radius will lead to more connections and a denser graph, while decreasing it will result in fewer connections and a sparser graph. Metric. The choice of distance metric can significantly impact the graph structure. For example, using a different metric like Manhattan or Chebyshev distances can lead to different neighbor relationships. Uncertainty methods. No explicit uncertainty methods are provided by the function itself. However, you can explore uncertainty in the graph structure by using different values of the radius parameter and observing the changes in the graph. Analyzing the distribution of neighbor counts across nodes and identifying potential outliers or areas with high or low connectivity. Challenges and fixes. Challenge 1. Choosing the appropriate radius parameter can be challenging. Sample use case. If the radius is too small, the graph may be disconnected, with many nodes isolated. If the radius is too large, the graph may become dense, with many connections, making it difficult to identify meaningful relationships. Fixes. Experiment with different values of the radius and visualize the resulting graphs to determine the optimal value. Use techniques like elbow analysis to identify a suitable radius value based on the number of neighbors or the density of the graph. Challenge 2. High-dimensional data can make it difficult to visualize and interpret the resulting graph. Sample use case in high-dimensional spaces. The notion of distance becomes more complex, and visualizing the graph can be challenging due to the increased complexity. Fixes. Use dimensionality reduction techniques like PCA or TSNE to reduce the dimensionality of data before constructing the graph. Explore alternative visualization methods like force-directed layout algorithms that can help to represent the graph in a more informative way.